Good morning, everyone. Welcome. This is one of the IEEE Communication Society talk series, and this is the ASU student branch chapter. And we welcome all of you. Aruzan is our chair. I'm just acting as the advisor. So today it's our great pleasure to have with us Professor Dimitrios Koutsonikolas from Northeastern University in Boston. Okay, the weather is not that nice over there, but that's okay. So Professor Koutsonikolas received his PhD in electrical and computer engineering from Purdue University in August 2010 and worked as a postdoctoral researcher in the same department from September to December of 2010. And currently he's an associate professor in the electrical and computer engineering department at Northeastern University and a member of the Institute for Intelligent Network Systems. Professor Koutsonikolas' research interests are broadly in experimental wireless networking and mobile computing. I guess you take a flavor from the title, with a current focus on 5G and beyond networks and applications. He received an IEEE Region 1 Technological Innovation Academic Award in 2019 and the University of Buffalo Teaching Innovation Award in 2018 and the University of Buffalo, School of Engineering and Applied Sciences Senior Teacher of the Year in 2017. So they have high expectations about your talk. It seems you are good in teaching. And the Early Career Researcher of the Year Award in 2015. The NSF Career Award in 2016. For those who are not familiar, the NSF Career is one of the most prestigious ones in the States. And also Best Paper Awards in IEEE Globecom 2023, ACM WinTech in 2022, ACM Millimeter Networks in 2019, IEEE WCNC 2017, and SensorCom 2007, and the Best Dataset Award in PAM, I'm not sure for the acronym, PAM. Good. In 2021. He has served as General Chair for IEEE Landman 2024. Actually, I give you a heads up, this year Landman is here at ASU, so if anyone is interested to submit a paper. Also, he has served as General Chair in IEEE WOMOM 2023 and ACM EWSN in 2018, and also in several conferences as TPC Chair, Technical Program Committee Chair. There are too many, so I'm not going to read them all. He is currently serving as Editor-in-Chief in IEEE Transaction Mobile Computing, and he's a distinguished member of ACM, senior member of IEEE, and a member of USENIX. So without taking more time, Dimitrios, the floor is yours.
Okay, can people hear me? Yes. Thanks, Irini, for the introduction. Thanks, Aruzan and the IEEE Communication Society branch at ASU for inviting me to give this talk. So today I'm going to talk about my group's efforts over the past 5 years to evaluate 5G performance in the wild over real operational networks. I don't know what's the style. Do I talk for 40 minutes and then questions, or people can interrupt?
For questions, you can. Typically, we ask them at the end, but if you overexcite them, they may ask you.
Okay, I'm happy to be interrupted anytime and answer questions. Okay, so feel free to ask. So 5G, okay, what's going on here? Yes, 5G was initially rolled out in 2019. Now we are in 2026. So we are past 5G's midlife at this point, right? Each cellular technology has a lifetime of roughly 10 years. So here we surpassed the midlife of 5G and we are heading towards 6G. So 5G came with a lot of promises 7 years ago. It promised ultra-high bandwidth and multi-gigabps data rates. It promised ultra-low latency also, sub-10 millisecond latency, or some people said sub 5 milliseconds. Some people even talked about sub-millisecond. And this ultra-high bandwidth and ultra-low latency created a lot of hype right? Even before the initial rollout. And many people thought that finally these new features of 5G, right, these capabilities would enable a new class of applications. So these applications are often called 5G killer apps. And let's see a few examples of them. So virtual reality for fully immersive digital environments. Augmented reality, where basically you overlay digital objects on real-world environments. Panoramic or volumetric video streaming for a fully immersive video experience. Connected autonomous vehicles, or CAVs, that enable real-time communication from vehicle to everything, to infrastructure, to a remote operator for teleoperation, to other vehicles, right? And finally, cloud gaming that can provide console quality gaming on any device. So all these applications have some common features. First of all, they are typically cloud or edge assisted. They require powerful edge servers or cloud servers to perform different computationally heavy tasks, such as SLAM, simultaneous localization and mapping for augmented reality, object detection for virtual reality or autonomous vehicles, frame rendering at high rates for video streaming or virtual reality. Second, all these applications exchange large data volumes with the cloud. And those exchanges can be uploading, right? Like uploading camera or LiDAR or radar frames to a server for object detection, or downloading high quality VR streaming frames or gaming frames or video frames, right, for watching on your headset or on your mobile device. And all these applications have stringent QoE, quality of experience requirements. For augmented reality, typically you need a rate of 30 frames per second minimum to have a fully immersive experience. For virtual reality, the requirements increase to 60 to 90 frames per second, and you have one more requirement, the motion to photon latency. The latency from the moment I do an action on my controller when I play a VR game, let's say I press a button to shoot, till the moment that the result of that action appears on my headset, that has to be less than 15 milliseconds to avoid dizziness. And finally, for autonomous vehicles, right, the end-to-end latency from the moment the LiDAR or camera senses an object till the moment, let's say, the remote operator sends a command to the vehicle, that latency has to be less than 100 milliseconds to avoid getting into life-critical situations, right, into accidents, for example. So all these 5G killer applications are both bandwidth and latency critical. Now, as I mentioned before, right, there was all this hype even before 5G was deployed. 5G promised, as Irini put it on her LinkedIn post a few days ago, everything everywhere, right? But let's see what is the reality 7 years ago. Does today's 5G fulfill its promise? And the truth is that soon after the initial rollout, right, we started seeing a lot of skepticism, criticism, or maybe even disappointment, right? And now 7 years after the initial rollout, and again, heading towards 6G, it's still not clear if 5G has really lived up to its expectations, the initial expectations. And all these concerns, all this skepticism is not without a reason. There are actually many challenges that, practical challenges that one has to address, right, to make 5G's promise a reality. So the first challenge is uplink downlink asymmetry. We often hear about 5G delivering multi-gigabps data rates, but 5G, similar to all the predecessor cellular technologies, is a highly asymmetric technology. You get gigabps data rates on the downlink. In the uplink, you get 1 or 2 orders of magnitude less, right? And many of the applications I showed before are actually uplink oriented. Second, 5G gets high bandwidth, high data rates by moving to higher frequencies, to mid-band or even to millimeter wave. But from physics, right? Higher frequency, higher attenuation, shorter range. So you get a coverage issue now. And then once you start moving, this shorter range means also more handovers, right? Since you have many small cells instead of one big cell, as in 3G or 4G, right? You have to do handover after handover, and of course, this disrupts the communication. Finally, the 5G ecosystem is much more complex than the LTE 4G ecosystem. You have many components. You have, of course, the devices, the radio access network, the core network, you have a bunch of new protocols, and also to support all these applications, new applications, now you have the applications themselves, software, edge and cloud servers that have to interact with the communication infrastructure. You have diverse frequency bands. Low band was there in LTE, mid band was also partly in LTE, but now it's heavily used, and millimeter wave, and soon people are talking about FR3, the band between millimeter wave and mid band. You have diverse architectures. I don't know how many of you have seen these two terms, SA and NSA, but the full-fledged 5G is standalone 5G. You use a 5G base station and a 5G core network. To speed up the deployment, many operators started with NSA or non-standalone 5G, which means we use a 5G base station, but the core network is still LTE, and that has some limitations. And even today, many operators are using still NSA, and the two architectures coexist. And finally, you have many and diverse operator policies in terms of resource allocation, which user do I serve under congestion, handovers, when do I do a handover, how do I do a handover, beam management, right, with millimeter wave, how do I switch the best beam, when do I switch to a new beam as the car moves or as blockages come and go, carrier aggregation, which cells do I aggregate to boost performance and when, and all these policies, of course, also impact the performance, but they are opaque to the user. So I argue here that because of this complexity, right, of this ecosystem, we need large-scale measurement studies for understanding the potential and limitations of today's 5G, and also to understand what we can improve and how to improve, right, for future deployments. So this is what my group has been doing for the past 5 years. We've been doing measurements of operational 5G over operational real-world networks across the country. We have done 6 cross-country driving trips from Los Angeles to Boston in 22, from Boston to Chicago and Atlanta in 23, again from Los Angeles to Boston in 24, and then from Los Angeles to Miami and from Boston to Los Angeles in 25. We also did 3 more multi-day trips in remote rural areas. We drove around Alaska, we drove around Maui, Hawaii, and we drove in New England from Boston all the way to the border with Canada, in Maine, Vermont, New Hampshire, to explore basically the digital divide. We did many more smaller measurement campaigns in select cities, and we collected multiple terabytes of data. We have released 11 open data sets so far, and there are more coming. What are the goals of these measurements? Not sightseeing, for sure, okay? We want to characterize 5G performance in the wild. We want to compare with its predecessor technology, LTE, but we also want to compare against another technology that emerged recently, right? Starlink, LEO, low Earth orbit satellite networks, which actually is viewed as an integral component of the upcoming 6G technology, but also as a competitor to 5G, especially in areas where we don't have good cellular coverage, right? We want also to study the evolution of 5G. We want to understand its limitations. Then we want to explore the potential to support this new class of applications, 5G killer apps. And finally, we're trying to uncover operator policies and their impact on performance. And this is important for another reason, because that can guide the design of test beds, emulators, simulators that mimic real-world performance. So I'm going to list here a summary of the work over the past 5 years, and I have divided it into 3 categories, right? Performance studies. We have done a lot of studies about cellular and Starlink performance under driving. We looked at 5G standalone performance alone and what are the benefits that it brings compared to non-standalone. We looked at the potential benefits of multi-carrier access if I had multi-SIM devices that have 2 or 3 devices together, right? And they can simultaneously connect to 2 or 3 operators. What are the benefits? Or if I have a device that can connect simultaneously to cellular and Starlink, what are the benefits? We looked at MIMO and carrier aggregation, 2 fundamental mechanisms for throughput enhancement, right? We are recently exploring video streaming over 5G and Starlink. Then there is another class of work where we look, as I said, at operator policies. We try to understand how operators allocate resources in millimeter wave networks, how they perform beam management in millimeter wave networks, and what configurations they use to enable handovers. This is the last one is also work in progress. And finally, the third class of work is not using active measurements by us. Here we do crowdsourced measurements. We write applications and give them to our collaborators in Europe, in US, both industry and academia, and also we collaborated with UCLA speed test. I bet many of you have used the speed test application on your phone to measure the performance of your network, right? So we got a 5-year data set from UCLA and analyzed the evolution and the evolution basically from the beginning of 5G till today. Actually, a couple of years ago, I asked Irini also to join in one of these crowdsourcing measurements, but none of her students was willing to do.
Some volunteers here.
So I'm not going to talk, of course, about all this here. I will give one example of a performance study and summarize a few results. And then also I will give one example of how do you study, how do you try to uncover operators' policies. Before that, let's take a look at the test bed that we use in most of our studies. So we have a bunch of phones, as you can see, in the car, and each of the phones connects to a different cellular operator. And now each phone connects also to a different device, another device called XCAL Solo. This is this green device that you see here. XCAL connects to the phone through a USB port, but it listens on the Qualcomm diagnostics port. And basically, imagine it as a super fancy, super capable sniffer. It captures all the signaling messages that are exchanged between the phone and the base station, and then it processes those messages and gives you hundreds, literally hundreds or maybe 1,000 KPIs, metrics, performance metrics at all the layers of the protocol stack. Okay, so that's how we get all the insights. Now, to run measurements and to test applications, we also need servers. So we deploy a bunch of Amazon servers across the country. Typically, we have 2 cloud servers, one on the east, one on the west coast. These are the 2 green circles here. And then we also deploy a bunch of edge servers. So Amazon has partnered with Verizon and they deploy something called wavelength server. These are servers attached to the Verizon cellular network. So your packets can reach the server without exiting the cellular network, okay? So these are optimized for edge computing. They have lower latency, right? So we deploy many in major cities. And as the car moves, right, it connects always, the phone connects to the geographically closest server. So this picture shows the GUI of this XCAL program, this XCAL tool. But also starting in 2024, we added one more component to our test bed. We have a 4th phone that connects to a Starlink dish, which you see on the other picture there. So the Starlink dish is mounted on the rooftop of the car, right? So that allows us to measure simultaneously cellular and Starlink performance. So I am going now to share some results from the first project, right? So let's see how cellular networks perform on the wheels when you are driving. And this was the first in-depth study of the mobile network performance of all 3 major US operators while driving across the country. So as I mentioned, we did that same route twice, 18 months apart, driving from Los Angeles to Boston. We used those XCAL devices. We collected a large and unique data set of cellular network performance that included both application measurements, diverse application measurements, and lower layer metrics, and all the signaling events. And then we studied different aspects: coverage, network performance, handovers, mobile application performance, and for the 2024 trip, as I said, we also put a Starlink on the car, so then we can also compare the performance of cellular and Starlink. So let's see a few results. Let's see basically 2 things here: how cellular performance really has changed over the between 22 and 24, and how does cellular compete with Starlink. So I'll start with coverage. These graphs show the coverage in the 2 years, right, with each technology. Each technology is represented with a color. LTE and LTE Advanced are 4G technologies, and then the remaining ones are 5G technologies, different versions of 5G. And the y-axis basically shows the fraction of miles during which we were connected to a given technology. So you can see that back in 22, that is already 4 years after the initial 5G rollout. The 5G coverage across the country was still at a rather disappointing level, right? Only one operator, T-Mobile, had more than 40%, about 70% 5G coverage across that route, along that route from LA to Boston. The other two operators had 5G only in 20% of the route. In 24, things improved a lot, as you can see. Again, focus on yellow, orange, and red. This is 5G, right? So things improved a lot. T-Mobile now offers 95% 5G coverage along that route. But still, in 2024, right, we are at 5G's midlife, and still 2 of the 3 major operators had 50% of that route from LA to Boston with only LTE service. Okay, so we're still a long way to go. Now, if we take a closer look at the 5G coverage, there are different types of 5G, right? So there is 5G low, and then there is high-speed 5G, which combines mid-band and millimeter wave. What we really care about is the high-speed 5G, orange or red color. This is the 5G that offers you high performance, okay? This is the type of 5G that different operators call it 5G plus, or 5G ultra capacity, or 5G ultra wideband on your phone, okay? In contrast, 5G low, the yellow part, just improves the range compared to LTE, but it doesn't give you any performance advantage. So if you look at high-speed 5G, you see that in 22, the percentage again was very low. Again, only one operator had about 40% coverage, right? The other 2 had less than 20%. In 24, things improved a lot, and now we see that 2 of the 3 operators had almost exclusively high-speed 5G across the country. The third operator, AT&T, still relies heavily on 5G low. Okay, so coverage has improved a lot in 2 years, but does this improved 5G coverage translate into improved performance? So here I'm showing again for the 2 years, 22 on top, 24 at the bottom. I'm showing the cumulative distribution functions of the downlink and uplink throughput of the 3 major operators. I use the colors to match the operator's logo, right, so that it's easier to see. So if you compare 22 with 24, again, you see a multifold improvement in throughput, right? In the downlink direction, if you focus on the median case here, you see that in 22 we had just a few tenths of megabps, right? In 24, we have a few hundreds of megabps, so that's an order of magnitude improvement. In the uplink case, the improvement is lower, but still substantial, from just a few megabps, right? Which is, imagine, very, very far from what 5G promised. We are now getting a few tens of megabps. Again, that's a big improvement, but that also shows the asymmetry of the technology that I mentioned at the beginning, right? We are talking about gigabps throughput. You can get that gigabps or hundreds of megabps only in downlink. In uplink, we are still very far from even going to 200 megabps in the typical case, right? Not in the extreme case. Okay, we also see that the operator ranking changed a lot from 22 to 24. In 24, there is a clear winner, right? Who is leading the field. Now, where does this improvement in overall cellular throughput come from? So in this table, I compare in 22 and 24 again, 3 percentiles, the 25th, 50th, and 75th percentile for each type of technology, for LTE, 5G low, 5G mid-band, and so on, right? And the last row, which is where you should focus on, shows the difference, right? Green means improvement from 22 to 24. Red means things got worse. So we see that there is an improvement in every technology, right? In fact, even LTE performance improved from 22 to 24. The only exception is millimeter wave, which is the only technology that can give you gigabits per second throughput. Here we saw a reduction in the performance. And the reason is because Verizon decided actually in 24 to stop limiting millimeter wave deployment in big urban centers, but also start deploying them on freeways in suburbs. And there, of course, the car speeds are faster. There are more mobility-related impairments, right? Millimeter wave is kind of difficult to work, so that resulted in lower performance. Now, if you compare the numbers, you will see that the biggest improvement comes in the mid-band, as expected. That's the main band for high-speed 5G. The improvements in the mid-band were 3 to 14 times for the three operators in 2 years, and those big improvements in the mid-band contribute to the overall improvement in cellular performance that we saw in the previous slide. Okay, so things are looking good. Maybe not perfect, but we are moving with fast rates towards better 5G. But performance, right, throughput is only one part of the picture. Remember, the applications that I showed in the first slides are both bandwidth and latency critical. So what happens to the latency? Again, this is the performance, the throughput result. Now, if I put the latency results next to them, we see a very different picture, right? The latency results have not moved to the left, to your left at all. So basically, latency has not changed practically at all in 2 years. And remember, 5G promised sub 10 millisecond latency. What is the median latency here? In both years, it's about 70 milliseconds, right? So we are very, very far from the promise in terms of latency. And remember, again, all these applications have certain latency requirements. If you want to run autonomous vehicles, remotely teleoperated vehicles, right, you need an end-to-end latency of 100 milliseconds. Well, even in 2024, we are not always able to meet this requirement. If you want to run augmented reality at 30 frames per second, you need an end-to-end latency from the moment your camera captures a frame to the moment the server sends back the object detection results of 33 milliseconds. That's here. Basically, we are rarely able to meet this requirement. If you want to run cloud-assisted or edge-assisted VR, you need a motion-to-photon latency of less than 15 milliseconds. That's the last line here. Basically, even in 24, we are never able to meet that requirement. Okay, we cannot run VR without getting dizzy over a cellular network. Any questions so far?
I want to ask, did the software or the hardware play a significant role also to this improvement?
Yes, that's a very good question. So are you talking about hardware and software, the telco hardware and software, or the application hardware and software?
Both.
So for the telco, of course, right, to get these improvements, you need hardware. You need better hardware. You need better carrier aggregation, which I don't have time to cover. You need MIMO, right, potentially. So yes. Now for applications also, the hardware and software plays a role, right? Your phone, of course, more advanced phones have better hardware capabilities, but we did a lot of studies about how the software can have an impact, right? For the same application, how you design the application, what software optimizations you put can have a big difference. And I'm going to show one example soon. We can discuss offline also about many other cases. We found cases where changing the design of an application, of SLAM, let's say, can have a big impact under the same network. Okay, so let's slightly change topic now, and let's try to see how cellular compares with Starlink, with LEO satellite networks, right? Remember that in our 24 cross-country drive, we had also Starlink on the top of the car, right? And we simultaneously measured cellular and Starlink performance. So first, let's talk about availability. So availability means how many times you are connected to that network. So in that cross-country drive, again, from LA to Boston, we saw that our cellular network phones were always connected to cellular. So 100% availability, no outage. With Starlink, we saw almost 100% availability. There was a 2%, especially when driving through downtowns of big cities, where Starlink could not get coverage because the tall buildings were obstructing the view. But it's still almost perfect, right? Across the country, I mean, it's 90% availability. Now, let's take a look at performance, downlink throughput, uplink throughput, and latency, or round-trip time. let's start with downlink throughput. So for downlink throughput, now I have added to the CDFs, the three CDFs of the cellular operators that I had before, I added a black line, and that black line corresponds to Starlink. And we can see that in terms of downlink performance, Starlink is pretty competitive, right? It performs very similar to the cellular operators. In the median case, it outperforms them by 25 to 80%. Where it really lags behind is the peak throughput, right? Starlink cannot give you hundreds of megabps or gigabps, more than gigabps throughput, right, which you get from cellular networks when you are using a millimeter wave base station. On the other hand, if you look at the uplink performance, you see that Starlink lags behind, clearly behind, right, all three cellular operators. So that's certainly an area of improvement for Starlink. But where Starlink excels, and that was initially a surprising result, is the latency. One would imagine that since the packets with Starlink have to go all the way up to a satellite and down again to a ground station, right, the overall latency to a server finally would be low, would be higher. But we can see that Starlink has the best latency compared to all three cellular operators. So to summarize, Starlink is indeed a solid competitor for mobile internet access, especially in rural areas where two of the three cellular providers still do not have good high-speed 5G coverage, right? Remember, only T-Mobile has about 90% of the route covered with high-speed 5G. So Starlink offers you almost 100% availability, lower latency than cellular networks, and similar downlink performance in the median case, but lower peak performance, and the main area for improvement, lower uplink performance. Any questions? Okay. So let's see how this performance now translates to application performance. Can we support these 5G killer apps? So we experimented with all the 5 applications actually that I show on the first slide, the second slide. But I'm going to show us to show 2 examples here. One uplink oriented and one downlink oriented application. So I picked augmented reality as an example of an uplink oriented application. So here we have an application running on your phone where basically your camera captures the surroundings and offloads those camera frames to a remote edge or cloud server. The server has a GPU and runs object detection based on DNNs, right? Identifies all the objects and sends the result back to the application, to your phone. Now, even today, there are no such applications on the market. There are augmented reality applications, but they have very simplified functionality. They don't do object detection using DNNs. So we had to build an application ourselves here to evaluate its performance. And we implemented this as an Android application. And also we incorporated another feature here called local tracking. So to understand local tracking, basically imagine that I capture a frame, I try to send it to a server, but by the time the frame reaches the server and the server runs the DNN and the result comes back, right? Maybe this doesn't complete in 1 frame's time. Okay, so then what do? I use the old result. That is going to result in low accuracy. So local tracking is a technique that tries to mask this latency. Basically, if the result from the server hasn't come back, I use the latest result, and based on the speed, I try to guess how the objects would move from frame to frame and move them, right? So that I don't have so inaccurate results, right? Let's say if Irini starts moving towards me, right? Every second, she's going to come closer and closer to me, right? So even if I don't have object detection results every time, if I know her speed, I can guess where she will be in every second, right? So that's called local tracking. So now, the main metric of interest here is the accuracy of object detection when it's done over an edge server or a cloud server compared to when it's done offline, when the data, the camera frames are readily available to the GPU. So we compare the accuracy with offloading with the offline accuracy, and this is a metric used in many works in computer vision. The goal is to get, with our application on the move, 90% accuracy, at least 90% of the offline accuracy. Okay, then we are saying we are satisfied with the result. Okay, so results for 22 and 24, 3 metrics, end-to-end latency from the moment I capture a frame to the moment the result comes back to the server. How many frames per second I can send to a server. And the accuracy, here we use again a metric from computer vision. It's called mean average precision. The details don't matter. What matters is the higher the better. Okay, 100% accuracy is the best you can get. So I also use 2 dashed vertical lines to mark the requirements. Our application was designed to operate at 30 frames per second. Remember the minimum requirement for a fully immersive experience. So that's here. That's here. And for 30 frames per second, the latency, the end-to-end latency has to be 33 milliseconds. That's here. And the other line there is the target in terms of accuracy, 90% of the offline accuracy for those scenes that we used here. Okay, so if you compare 22 to 24, you see a substantial improvement in 24, okay, but very far from satisfactory still. We rarely meet the accuracy threshold, okay, when we are on the move. You want 30 frames per second and you offload at most 10 frames per second. You want a latency of 33 milliseconds and your latency is, well, up to more than 1 second sometimes. Okay, so very far from satisfactory. Now, what can we do to improve things? Well, actually, before that, first, if you look at Starlink, Starlink has the worst performance, actually, right? Worst accuracy, worst number of offloading frames, longest latency. Why? Starlink had the lowest latency, if you remember, right? But remember, in addition to the lowest latency, it also has by far the lowest uplink bandwidth, and this application really needs high bandwidth to offload camera frames. Okay, so what can we do to improve things? Well, these results were with raw frames, uncompressed frames, which require a lot of bandwidth. So the simplest thing you can do, right, and it's something that people do a lot these days, is compress the frames, right? Then your bandwidth requirement reduces. So here we see much better performance in both years. For Starlink, still we see that we almost approach now the target accuracy, but still we are not there. But with cellular networks now, you see that in 24 at least, we cross the target accuracy 25 to 50% of the time with different operators. So we can enable now, not always, but we can enable augmented reality, this kind of challenging augmented reality applications while on the move. And this is in spite of the fact that I'm still offloading at most 12 frames per second instead of 30. And in spite of the fact that my latency is still a couple of hundreds of milliseconds instead of 33 milliseconds. So here is where compression and the other technique that I described before, local tracking, really help, right? Even though the network is still not ready to give you the quality of service you want, you can get the quality of experience you want half of the time because of these software optimizations, right? And that's the main takeaway from this slide. The network has improved a lot. The bandwidth has improved a lot, but even in 24, 5G's midlife, we still need software optimizations that were introduced 10 or 20 years ago, right, in the pre-5G era to make these applications work. And we're going to need this kind of software optimizations for quite a few years, even in 6G, right? We're very far from just taking a very basic application without any software optimization and running it over a wireless network. Okay, next application, next example, 360-degree video streaming, panoramic video streaming. This is a downlink-oriented application. Here we used an open source video server and a custom-built player again, and we used 4 bit rates to encode the videos in 22. We added 1 more bit rate in 23. So here we use as a main metric the quality of experience based on an equation from a paper developed by your department chair a decade ago. That's one of the most famous papers in video streaming, right? It says that the quality of experience depends on the bit rate of that segment. The higher the bit rate, the better. Depends on the smoothness, how different is the bit rate of the current segment versus the previous one. In plain English, this means it's better to watch a video in mediocre quality throughout the time rather than switching between very good and very bad quality, right? That is going to disturb, to frustrate the user. And it also depends on the rebuffer time. Basically, how much time your video is frozen and it just rebuffers. Okay, so here 3 metrics, the QoE that I just showed, the bit rate and the rebuffer time, the fraction of time during which the video was frozen and was rebuffering. Again, for 22 and 24. If you compare the graphs, you see again big improvements in 24, right? Let's look at the rebuffer time. Here, half of the time your rebuffer time was 20 to 50%. Here, your rebuffer time is also often 2 to 5% only, right? The bit rates also have increased a lot. And of course, the QoE, you no longer have those huge negative QoE values, right? Your QoE often exceeds 0, is positive. If you look at Starlink here, you see something interesting. Starlink has the lowest stall rate, the lowest rebuffer time, but also lower bit rates than 2 of the 3 cellular operators. And if you look at the QoE function, you see that Starlink has the most steady, the most stable QoE, right? Its best value, it's lower than the cellular best value, but its worst value, it's much better than the cellular's worst value. So much more stable performance. And why is that? Remember that Starlink has a much lower peak value compared to cellular, right? So with cellular, you enter a high-speed 5G cell. Suddenly your player starts requesting video at high bit rate. But then soon you drive out of that cell to an LTE cell or 5G low band. And then what? Then you get a stall, right? Because that bit rate can no longer be supported. So Starlink has a much more limited bandwidth, which means, yes, lower bit rates, but also lower chance for stall when you overshoot and request a high bit rate. So I will quickly now show an example of a different kind of measurement studies. Instead of just measuring performance, we try to uncover some policies. And typically these policies, again, are implemented on the base station. That's a black box for us. We don't have access to the base station. So we try to infer those policies, right, by doing experiments. So the case I picked here is resource sharing for millimeter wave networks. So millimeter wave can give you up to 4 gigabps downlink data rates, which means that even a single flow can completely overload the base station, right? So that's why resource allocation is important. Now, I don't know if the department offers a cellular network or a wireless network class here, but basically in many of this type of classes, you learn that in cellular networks, proportional fairness is the de facto standard of how you do resource allocation. And proportional fairness in plain English means that I try to maximize my capacity, but at the same time, make sure that nobody starves, okay? So users who have good channels should get more resources, better throughput now, but we should never completely penalize, we should never starve completely a user, even if that user has a bad channel, okay? So what about practice though? Do operators use proportional fairness in practice? So we conducted the first systematic study of this kind of allocation policies, right, through measurements in 4 cities and 2 operators. T-Mobile doesn't use millimeter wave. And I'm going to summarize a few of our findings here quickly. So I will start with a basic motivational experiment. We have 2 devices. One user is moving around the base station like I'm moving now. The other user is always facing the base station. Assuming the base station is there, it holds the phone like this, right, facing the antenna always. So the capacity in this case was 3 gigabps. And here we see a timeline. When both users have good quality, they share the capacity equally, 1.5 gigabps each. When one user starts moving and its throughput drops, with proportional fairness, the other user should get this lost capacity so that we maximize. We still utilize 3 gigabps. You see that that's not the case. The good user never gets more than half of the capacity, right? So that's a proof. Again, you cannot rely on this graph. Repeat this in many locations, in many cities, with both operators. The result was the same. So that's a proof that operators do not use proportional fairness in practice. They use simple threshold-based policies. So what are those policies? We found some common policies for both operators. One is fair sharing among backlogged flow, backlogged flows. A backlogged flow is a flow where the user is trying to download as fast as possible. Okay? So in this case, the operators share the capacity. Here I'm showing for two operators and different cities. The different colors are different phones, different devices. You see that the height of each color is the same, right? So basically, when we have 3 gigabps, the operator gives 1 gigabps to each of the 3 devices. Okay? The second interesting thing we found is over-provisioning of resources. So that means that when a new device requests a certain amount of resources, the operator gives more to this. How did we do that? We had a gray device that tries to download as fast as possible, and then there is a yellow flow that comes and asks gradually more and more, 10 Mbps, 25 Mbps, 50 Mbps, and we see how much the network takes away from the gray to give it to the yellow. So let's take an example here. When the yellow flow requests 10 Mbps, the throughput of the gray flow reduces from 2 gigabps to 1.7. So 300 megabps are taken away from one flow and given to the other flow that simply asks for 10, right? That's the over-provisioning. We also found differences across operators, but more interestingly, also across cities for the same operator. The first obvious difference that you can see probably by observing this set of figures is the capacity is different in different cities. In most cities back then, we saw 2 gigabps capacity. In Boston, we saw 3 gigabps capacity. Nowadays, you see 4 and even 4.5 gigabps capacity. The second difference is if you look at these graphs, you see that the amount by which the gray flow reduces for a given yellow flow demand is different again, right, in different cities and operators. So I used before this example. You ask for 10, you get 300. But look what happens in Boston. You ask for 10 and you get maybe 20 or 30, not 300. So in Boston, the same operator is much more conservative in allocating resources to a new flow compared to, what's the city? Indianapolis. Finally, a third policy is about how do you deal with new flows which come to the network with some substantial demand. So here again, we did another type of experiment. The gray flow, as before, requests backlog traffic. I want to download as fast as possible. You have a yellow flow that has a constant demand of 500 megabps, and then you have a black flow that keeps increasing its demand, 200, 500, 700, and so on. So look at the yellow flows throughput in these figures. In most of the figures, in most cities and operators, the operator squeezes both the gray flow and the yellow flow to accommodate the demand of the black flow. In Boston, you see that the height of the yellow flow is unaffected. The operator punishes only the backlogged flow that demands a lot of resources and not a flow that has a constant non-backlogged demand. Okay, so again, the same operator can have different rules in different cities. So I'm almost done. So this is a summary of our recognition for this work. So we got the Best Dataset Award for the conference that Irene was trying to pronounce. And last year, we were runner-ups for the Community Contribution Award in ACM Connex. And we share these results with many industry partners, right? We're currently collaborating with Rakuten and AT&T. And we also shared our results to T-Mobile, and they acknowledged some of them, but they refused to give us explanations of why. So, okay, that's a different thing. So I have just 2 slides to finish to discuss a little bit the challenges if some of you want to do wireless measurement research generally and large-scale cellular measurement studies more specifically. So a few challenges here, right, if you want to get into this domain in wireless measurements in general. It's tough to decide, and that's the first step, right? You have to decide what and how to measure. Somebody can think, okay, we can evaluate 5G across the country. We'll get in the car and start driving, right, and have fun. Well, no, that's not the case, right? You're going to end up with a few hundreds of thousands of metrics. So you really have to carefully decide what makes sense for that particular study, what you will focus on, right, how to isolate, and so on. The other example, the second example I showed here, we knew what we want to measure. We want to measure resource allocation. But how do you measure it, right? You cannot go and see the policies on the base station side. So you have to design the experiments in a systematic way, have one gray flow, add another flow with gradually increasing demand, right, to try to infer the policies. The second thing is, well, related to this. Wireless networks are black boxes. You can't get in easily. On the device side, well, there are hardware like the Xcal Solo that we use. If you can afford it, typically they cost a few tens of thousands, right? But if you can afford it, then yes, you can get visibility. On the network side, not so easy. Back in my time as a PhD student 20 years ago, at least we could do Wi-Fi research. There were many open source Wi-Fi drivers, Linux drivers. Many people were doing research back then. Nowadays, both Wi-Fi access points and, of course, cellular networks base stations are completely closed for the user. So again, you go back to the first challenge, how to design experiments to infer the behavior. Third, infrastructure and platform gaps. Many times, test beds are not there, applications are not there yet on the market, so you have to build your own test beds and your own applications to do research, and that takes time. And if you want to focus specifically on large-scale cellular measurements, well, the main challenge here is data. Again, it might sound easy to get on the car and drive across the country and get data, but you end up with terabytes of data after every trip, right? You need, of course, storage, and you need coding skills, efficient measurement, and processing pipelines to automate the measurement process and also deal then with terabytes of data. Assessing end-to-end performance is hard, and there are all these factors that affect the performance. And again, you cannot just look at all of them. Here, I just summarized the results where we didn't look in depth at each of these factors, but then we have individual papers where we try to understand the impact of each of these factors, right, on performance. And that's not a simple thing to do. Again, when you deal with terabytes of data, you have to isolate some factors, you have to correlate some factors. So here, having statistics knowledge helps. And finally, you get many unexpected issues, and some of them are funny, but they do happen. So hardware and software failures. The car may break down in the middle of the night, and yes, it happened to us. Your Starlink dish might fly away while you're driving, and yes, this happened to us last month. Suddenly, we saw through the mirror the Starlink flying, and we were very lucky that it didn't land on the car behind us. Otherwise, I would be facing a lawsuit now. So you have to always be prepared for the unexpected. Plan very carefully, put many checkpoints when you try to automate the code, right? On one hand, you want to automate because you cannot just keep pressing buttons when you drive for 8 days. On the other hand, things can go wrong anytime. So your code has to be always fault tolerant, right? Bulletproof, with many checkpoints, with many backups, and so on. So in general, if you want to work in this area, you need a combination of strong system building skills, and that means both hardware and software. We build test beds, and we write code and applications, and we parse huge data sets, and analytical skills, and a lot of patience and persistence. So this is a list of my collaborators for this type of work, for the measurement studies over the past 5 years. And this is my lab today, basically consisting of 1 postdoc, 5 students, out of which 1 is about to graduate, and 3 junior students joined this year, and then 4 master students and 1 unpaid intern. Not all of them work in measurement studies. We have other projects that I'm happy to discuss offline. And I will finish with 2 pictures from our first trip back in 22 at the beginning and the end of the trip. And just to see if everybody is still awake, I'm going to ask you to find the differences between the 2 pictures at the beginning and the end of the trip. And here I have, if any of you are interested, this is a QR code that takes you to a website where we have all our measurement-related papers and all our open data sets. And we do hope that some of you will use your data sets, our data sets in your own research. And we are happy to answer any questions related to the data sets. Thanks, and I'm looking forward to listening to the differences or to answering any questions. Thanks again.